Swayam Prabha. Digital India. Educated India.
I'd like to talk to you for a short while today and cover a topic which has been coming up over and over again, but I thought I would do this from the beginning because there are several students here who have not had a background in it. And that has to do with matrices and Pauli matrices. So I'm going to write, I'd like to title this talk something like everything you wanted to know about Pauli matrices but were afraid to ask. So let's start in the beginning. I presume all of you know what an n by n matrix is. It's an array of numbers with a certain rule of addition of these objects, of these arrays. Does everyone know what a column matrix is? N by 1, n rows and 1 column. And a row matrix? 1 row and n columns, right. And you know how to multiply two matrices, they must be compatible with each other. You can multiply an n by m matrix by an m by k matrix and get an n by k matrix. Yeah. Okay, that's the only information I'm going to use. Now matrices, and we will specifically stick today to 2 by 2 matrices, although a lot of what I'm going to say is applicable in general. I'll tell you what's not applicable in general. 2 by 2 matrices are the most common things, and you've already heard a lecture by several people, Professor Lakshmi Bala and Prabha Mandyam, which used 2 by 2 matrices, and they spoke about qubits and then gave examples of 2-level systems and 2-level atoms and so on and so forth, and spin half, etc., etc. So I'm going to tell you all the properties of Pauli matrices today. They're a very special set, but I'll start by asking what's so special about it, why is it so special, etc., and then we will go on from there. Okay. If I were to write a matrix like this, a 2 by 2 matrix, it has 4 elements which could be real or complex. I don't make any distinction. If it's complex, there are 8 real numbers specified in this matrix. Otherwise, there are 4 real if you restrict to real things here. This is actually shorthand for a certain expansion, although you're not told that's the case in that as many words. It's actually a shorthand. You know what a linear space is, a linear vector space is. Just a set of rules for elements in which an operation called addition is involved. You add 2 vectors in the space, you get 1 more vector. You multiply by a scalar, you get another vector, etc. Notice that in this definition of linear vector space, at no stage is multiplication brought in. That's an extra that comes later on when you say inner product, outer product, the scalar product of 2 vectors, the cross product of 2 vectors in 3-dimensional space, and so on. All that comes later. In the beginning, you just have the addition rule for vectors and multiplication by scalars. That's all you need for linear vector spaces. So the word vector is a misleading notation there because it applies to more general objects than vectors alone. For instance, functions which are integrable between -infinity and to +infinity, they form a linear space. So mathematicians don't even like to call it linear vector space. That's an invention of physicists. It should be called a linear space. That's all it is. Okay. 2 by 2 matrices are also part of a linear space, the space of 2 by 2 matrices. N by n matrices are part of a linear space, the space of n by n matrices, because this object here actually is shorthand for the following: A times 1 0 0 0 plus B times 0 1 0 0 It is actually shorthand for this expansion here in a basis set, and this is the basis. That's the most obvious basis that you can think of in 2 by 2 space, in 2 by 2 matrix space. Mathematicians always look at the simplest possible descriptive term for anything. What would you call such a basis? That's the basis that occurs to you first. It's called the natural basis. It's the most natural thing that you can think of. Okay, but it's not a very convenient basis, and we'll see why that's so. But that's the obvious basis. Coefficient scalars multiplying the vectors. So matrices, strangely enough, n by n matrices for instance, have two kinds of characters. On the one hand, they will act on n by 1 column vectors and give you other column vectors. They will therefore represent operators. On the other hand, they will themselves be part of a linear space. And we are looking at it in the second sense now. So, I am going to look in the rest of this lecture, I am going to look at this 2 by 2 matrices as elements of a linear space of 2 by 2 matrices themselves. And then you can ask, are there operators which act on these matrices to give you other matrices? And the answer is yes. If you like, you can call them super operators and so on. But we are not going to talk about that now. We are going to just talk about the basis sets involving 2 by 2 matrices here. Now, clearly, just as in the case of, are you familiar with the concept of a basis in a linear space? That's the first thing that should have been told to you. A basis or a basis set in a linear space is a set of elements in terms of which you can expand any element as a linear combination. So, if you have a set of vectors which are special, a set of elements in a linear space which are special, such that you can take an arbitrary element of this linear space and expand it in a linear combination of this set of elements. Most common example, the vectors I, j, k in 3-dimensional space. These are unit vectors in 3 dimensions in Cartesian coordinates, and they form a basis in this space. In 3 dimensions, you need a basis set containing 3 independent vectors or elements, and they are these 3 guys here. Is the set of real numbers on a line, is the number line, is that a linear space? Yes, it is. You add 2 numbers, you get another real number. And there is an identity element, you add anything to it, it remains the same, namely 0. Under addition, we are not talking about multiplication at all. So, points on a line form a linear space, a linear vector space if you like, but that name is so misleading. Do points on a plane form a linear space? Yeah, they just ordered sets of 2 doublets of numbers, so they form a linear space. Do points in 3-dimensional space form a linear space? Yes. Yeah, so all these are linear spaces, R1, R2, R3, ... All these are linear spaces with their own basis sets, etc. Now, let us come to 3-dimensional space and ask, what does this basis do? What is so strange about this set of properties? Okay. What is required for a set of elements to be a basis set? Two things are needed, and they are different things altogether. They are mutually exclusive in some sense. The set must be linearly independent and 2, the set must span the space. Two qualities are needed for a set of elements to be a basis set. They must be linearly independent and they must span the space. Then and only then does the set form a basis set in the space. Okay. What do I mean by this? Linearly independent means none of the elements of this set can be written as a linear combination of the others. Can I write I as a linear combination of j and k? No. So, I, j, k are linearly independent of each other. Okay. They must span the space. In other words, intuitively, no direction should be left out. So, let us look at R3. Let us look at Euclidean space in 3 dimensions. And I claim to you that the set of vectors I, j, k form a basis, because none of them can be written as a superposition of the other 2. That is very clear. And secondly, these 3 vectors between them span the space in the sense that no direction is left out in this space. Any direction can be written as a linear combination of these three fellows. So now tell me, is this linearly independent? I, j, I plus j over root 2. 3 unit vectors in 3-dimensional space. Do they form a basis? Are they linearly independent? No, because this fellow is written as a combination of these two. Do they span the space? No, because nothing along the z direction is written in terms of these two guys. So certainly this not. So they satisfies neither linear independence nor spanning the space. How about this? Do they form a basis? Why not? I'm going to throw this out. How about these three? How about those three? They do form a basis. Are they linearly independent? Can any of them written completely as a linear combination of the other two? No. So they are linearly independent. Do they span the space? I have chosen I and j. They do span the space. So I have chosen I and j, and I have chosen k along some crazy direction like that. Why not? I never said the basis has to be orthogonal. That's the next property. That will come later when I say that they will be perpendicular to each other in some sense. We have not even talked about multiplication as yet. So is this completely clear? How about this? I, j, k, I plus j plus k. How about these four? I don't have to even normalize the set of basis vectors. They don't have to have unit magnitude at all. Is that a basis? Do they span the space?
Yes.
Yes, they span, but it's not a basis, right? How about this?
Yeah, it's a basis.
Is it a basis? Do they span the space? Yeah. So you see there are possibilities where the set of vectors spans the space but is not a basis because its no linear independence is gone. On the other hand, it may be linearly independent but may not span the space. How about this? I and j in 3-dimensional space. Why not? They are linearly independent but don't span the space. Okay? How about this? Do they span the space? Yes, they do. But are they linearly independent? No. You need both in order to have a basis. Yeah.
Sir, could we say that if we had an n-dimensional linear space and we have a basis set that it's not necessarily a basis set, we have a potential basis set that has n elements in it and all of them are linearly independent, then automatically they span the space because you can find components along every
depends. You have to check. You have to check whether they span the space or not. So you have to actually have a criterion for when it spans the space. Just saying in words that they're independent. We know intuitively in 3 dimensions that you need 3 different directions and so on. They need not be perpendicular to each other, but the 3 vectors cannot be coplanar. The moment the 3 vectors are coplanar, it's not a basis anymore because it's not spanning the space. So in some sense, you have to have a criterion by which the n vectors that you suspect to be a basis really is spanning the space. And that's a condition called the Gram determinant. What you do is the following. If A, B, C, D are all the vectors you're talking about, then you take this A dot A dot B, A dot C, B dot A, etc. like this. You take this determinant and it's called the Gram determinant. and you have to show that it's not 0. If this determinant is non-negative, if it's non-zero, then it's they form a basis. They can form a basis. Okay. Physically, you can ask what's the meaning of this condition. Let me ask you: in a plane, when would two vectors form a basis in a plane in 2 dimensions? They don't have to be perpendicular. I can choose oblique coordinates.
No, sorry. I'm just reading out what's there. Now, like you said, that wasn't a basis set, right? Because the last one isn't linearly independent.
Yeah.
Yes, sir. But like we can define everything with just the first 3, right?
Yeah.
I can. So,
Yeah.
So
Yeah.
why not like?
I should have done that. I
why
didn't
can't
do
it
it.
be a basis then?
They form a basis. IJK form a basis, very much so. That's a natural basis.
Yes, sir. But then you told like when you add the fourth one,
I said that.
No, when you add the I plus J plus K cap to this one,
Yes.
you said it doesn't become a basis set.
No, I didn't say it's a basis. I said it's not linearly independent.
Okay.
This is not linearly independent of these. Therefore, this doesn't form a basis set. Fine. It's over complete in some sense. It's complete and then there's something else to it. I don't need that as a basis vector.
Yeah.
I could have done this. I could erase one of these guys and that's a basis. That's now a basis. Agree?
But the third one still depends on I and J.
Can you write it uniquely as a linear combination of I and K?
Sorry, sir?
Can you write I plus J plus K as a linear combination of I and K?
No.
No, you can't because there's J sitting in there.
That's we.
So they are linearly independent. They are not perpendicular to each other, but I never said the basis set has to be orthogonal. Now for the next statement, given a basis set in an n-dimensional linear space, there is a procedure by which you can make the vectors mutually orthogonal. The way you do it is if the basis set contained in 3 dimensions, for example, if it contained 3 vectors which do not form an orthogonal set but they are not at right angles to each other, then you start off by saying I'll choose this vector first and take this vector and project its component along this and subtract that part out. Then I make this guy perpendicular to this fellow like this. And then I take the third vector, project it along these 2 directions, subtract those vectors out and make it perpendicular to the remaining 2. And it's called Gram-Schmidt orthonormalization. It's a big word for a very small, trivial concept. Okay. So now we are clear about what is meant by a basis set. It must span the space and be linearly independent. Yeah.
Sir, is there any statement which has been proven which says that to have for an n-dimensional space you have to have a minimum of n basis?
Yeah, the
elements.
dimensionality of a linear space is defined as the number of elements in a basis set. That's the definition of what yeah.
Sir, so what is the physical significance of the grand determinant?
Good. I was going to get to that. The physical significance is when do you have a basis set in 2 dimensions? Let's look at that. When you have 2 vectors, can they be parallel to each other? They wouldn't. They should be non-collinear. In 3 dimensions, they should be non-coplanar, etc. Right? So what should not be 0 for 2 vectors to be in 2 dimensions to be non-linear, non-collinear? Here's a vector, here's a vector. In 2 dimensions, in a plane, the plane of the blackboard. Do they form a basis set? Yes, in 2-dimensional plane, they do form a basis set. So what is non-zero about this set? The parallelogram has non-zero area. 2 vectors are non-coplanar in a plane, non-collinear, if the parallelogram formed by them has non-zero area. In 3 dimensions, the parallelepiped formed by the 3 vectors should be non-zero in area. So they cannot be coplanar. So in n dimensions, the hyperparallelepiped formed by these n vectors should not have 0 volume. If it has 0 volume, you are finished. Okay, so it's a very simple geometrical concept here. Okay. All right. Now that we have understood what a basis set is, let's ask in the space of 2 by 2 matrices what kind of basis set we can form. So I said if you took A, B, C, D, the same matrix, I write it as A times 1 0 0 0 plus b times 0 1 0 0 . This forms a basis set in the space of 2 by 2 matrices. But there is another basis set which is more useful than this set. This is the natural basis. That's the way you write. When I write a matrix, that's what I mean. They never tell you what basis you are writing the matrix in, but it's implicit that the natural basis is used. Otherwise, each time they have to specify that. Okay? But there is another term basis in which it's used, and that involves the Pauli matrices. It involves a unit matrix I sigma 1, I'll call sigma x what Lakshmibala called sigma x, I'll call it sigma 1, because I want to introduce this as a more general concept than the spin half operator. So sigma 1 is 0 1 1 0, sigma 2 is 0 minus I 0, sigma 3 . And I claim that this can also be written as A1 times I plus A2 times A0 times I plus A1 times sigma 1 . You can also write any 2 by 2 matrix as a linear combination of I need 4 of them for the basis. That number cannot be changed. I already mentioned that the basis set, the dimensionality of a linear space is the number of elements that a basis set has. And the basis is not unique, of course. Just as in 3-dimensional Cartesian coordinate space, in Cartesian coordinates, you could have a set of axes like this or like this or like this. They are all basis sets. But the fact that you need 3 basis vectors is not to be disputed in 3 dimensions. How do you define an infinite dimensional linear space? Well, one way to say is that the number of basis element vectors must be infinite and so on. A better way of saying it is it has no finite basis. And infinite dimensional spaces are things which you use all the time. We've not talked about it yet, but we will. Yeah, there was a question.
So you've written A naught I plus A1. Those are the A and A1 are all the elements of the matrix that we have.
It's going to become. So what's this become? What does this line become? Write down those vectors, write down those 4 matrices, multiply by these scalars and tell me what the first element is. For starters, she already mentioned that these are Hermitian operators, Hermitian matrices. So the basis set is Hermitian for reasons which will become clear. We'll see. So what happens if I write it like this? What do I get? The first element, this has a 1. So it's A naught. That last guy has 1 there. What happens here to A1 sigma 1? There's an A1 which acts on this and gives you an A1, and then there is an A2 which acts here, so it's A1 minus IA2, and this is A1 plus IA2. So this matrix is formed by taking these 4 guys and adding them up. And that must be equal to this. So what are the equations that make 2 matrices equal? When are 2 matrices equal? When each element of the first is the corresponding element of the second. Because I'm writing the same matrix in 2 different bases. It's the same vector, same element. Therefore, they must be equal component by component. A equal to A naught plus A3. B is equal to A1 IA2. C equal to A1 plus IA2, D equal to A0. Yeah. So tell me, what sort of equations are these? They are linear simultaneous equations, right? Do you agree that if I give you A0, A1, A2, A3, you will be able to find A, B, C, D from these equations? They are linear equations, so they are invertible. Do you agree that if you give me A, B, C, D, I can find A0, A1, A2, A3? What are the equations? A plus D over 2 is A0. What is A1? So if you give me A, B, C, D, I tell you A0, A1, A2, A3. If you give me A0, A1, A2, A3, I tell you what A, B, C, D is. Uniquely. I've gone from one basis to another. So I've proved that you can take any 2 by 2 matrix and write it as a linear combination of the unit matrix and 3 Pauli matrices. A3 is what? D minus B? No, A minus D is 2A3. So this is okay. Oh, sorry, this is A3. A2 is what? C minus B over 2. Okay. Now we got to ask, what's the advantage of doing this? What's the big deal here? Okay. First thing you observe is that if the matrix A, so let me call the matrix M, let's call it, right? What is the trace of M? A plus D is the trace of M. And A plus D appears here in A0. If the matrix has 0 trace, what can you say about it then? If it so happens that the trace of the matrix is 0, then in this expansion you don't need A0. Therefore, a traceless 2 by 2 matrix can be written as a linear combination of the 3 Pauli matrices uniquely, if it's traceless. That plays a role too. Okay. Now, what are all the wonderful properties we can talk about here? What happens if I square this basis vector? What's the square of this basis vector? The square of this, what's the square of this basis vector? Do you know the row by column rule for multiplying 2 matrices? What's the square of this matrix? 0, it's a null matrix. So it's awfully inconvenient in further work. You have a basis vector whose square is 0. It's losing information in some sense. Ditto for this guy. Not a convenient thing. So let's look at all the advantages of the Pauli matrices. All the 3 Pauli matrices have 0 trace. Observe that. So if a 2 by 2 matrix has a trace, then I know that it's not made up of the Pauli matrices. Yeah.
Sir, so let us take, for example, let us in the normal basis, in the natural basis, if we are representing matrices with only real numbers, then when we are using the poly matrices as a basis, then won't we be unnecessarily including complex numbers?
Yeah, it's not unnecessarily. We'll be including complex numbers, but all this is nothing to do with real or complex. It's valid for real or complex. It doesn't matter. I never said anywhere that A, B, C, D must be real.
No, but if in our initial space,
Yeah.
initial linear space, we used only real numbers as entries from A to C.
Yeah,
Then here, when converting them, we'll have to start dealing with complex numbers.
yeah.
Won't that become a little bit more?
No, on the other hand, introduction of complex numbers is a great help. Real numbers are sort of incomplete in some sense, in hundreds of senses, in the rigorous mathematical sense. It's very helpful to extend things, real numbers to complex numbers. It's useful all the time. There's nothing imaginary about an imaginary number. There's nothing real about a real number. They happen to be historical names which are given in a very ridiculous manner, but we are stuck with it. There's nothing imaginary. There's nothing physical about a real number and unphysical about an imaginary number. A complex number is a real pair, an ordered pair of real numbers with certain rules of addition and multiplication. That's what a complex number is. And all physical quantities, incidentally, are complex numbers. The refractive index of a medium is a complex number. The dielectric constant of a medium is a complex number. All these are complex numbers with the real and imaginary parts having different physical significances. In the case of the refractive index, the real part measures the amount of dispersion and the imaginary part measures the amount of absorption. And they go together in all physical systems. So all response functions are in general complex numbers with specific physical significance. Okay. A function of a real variable may be once differentiable or not differentiable at all, or twice differentiable, thrice differentiable, etc. When you extend it to complex analysis, an analytic function of a complex variable is infinitely differentiable. If it's differentiable once, it's differentiable an infinite number of times. You see the great advantage? Whereas in real numbers, you don't have that advantage. If it's not differentiable once, it's not differentiable the second time, of course not. Yeah. But you can't tell by looking at the first derivative. For instance, if you look at a function like f of x equal to x modulus x, what does this function look like? This is x squared if x greater than 0, minus x squared if x less than 0. So it's like taking a parabola, sticking it here, and taking the other half of the parabola and sticking it here. It looks like a cubic curve. The slope here matches. The function is continuous, there's no problem. The first derivatives match because it's 0 at the origin on both sides. But the second derivatives don't match because of this guy. And you don't know it by looking at it, unless I write this explicitly down. Okay. In complex analysis, you don't have this kind of mess. So let's look at all the properties of the traceless determinant equal to minus 1. Are you familiar with the Hermitian conjugate of a matrix?
Yes.
In matrices, unlike numbers where you take a complex conjugate of a complex number by setting all i's to minus i's, in the case of matrices, it's not very useful to take the complex conjugate of a matrix. It turns out it doesn't have that many interesting properties. What has interesting properties is the complex conjugate transposed. So you take the complex conjugate and then you transpose the matrix, or do it in either order, it doesn't matter. Okay. So what's the complex conjugate of this? It's denoted by dagger. So let's write it properly. A star, D star, C star, B star. Determinant is minus 1. And Hermitian. When is a matrix Hermitian? When it's equal to its Hermitian adjoint. This is called the adjoint of the matrix. M equal to M dagger implies M is Hermitian. What's the use of a Hermitian matrix? Well, it turns out that in quantum mechanics, when you represent physical quantities by matrices in certain situations, you would like these quantities, if they are quantities which take on only real values, you would like to have them represented by operators or matrices which are Hermitian, because a Hermitian matrix has only real eigenvalues. Does everyone know what the eigenvalue of a matrix is? Yes? Again, it was mentioned briefly, but does anyone not know? This is the time to stop and tell me. Why are you hiding this ignorance? They proudly say, I never heard of eigenvalue. It's a trivial concept. It can be straightened out in 2 seconds. Okay? It's like hiding your toothache from a dentist. It's self-defeating, okay? If you take a matrix M, which is n by n, say, n matrix, and it acts on vectors which are column vectors, n rows and 1 column, that's the kind of vector it acts on. Let me call that U. What's a 1 by 1 matrix, by the way? Just a number. Just a number. Real or complex, we don't care. Just a number. Now it turns out that when an n by n matrix acts on a column vector, n by 1 column vector, it will give you an n by 1 column vector on the right hand side. And if it so happens that this is a special column vector, so special that m acting on it gives itself back, multiplied by a possible multiplicative constant. This constant is called the eigenvalue. This vector, special vector M, U, is called an eigenvector or an eigenstate in quantum mechanics, or an eigenfunction when you talk about functions. And this is your operator or matrix. But for the present purpose, it's matrix times eigenvector is equal to eigenvalue times eigenvector. This sort of thing is called an eigenvalue equation. An n by n matrix has n eigenvalues. We will see why that is so in a minute. It has n, no more than n, no less than n eigenvalues. They could be real or complex numbers. We don't care. They could be repeated. But if you separate them and count them separately, you have exactly n eigenvalues. And the most general possibility is when you have complex numbers as eigenvalues. Sometimes the vector does not have n eigenvectors, the matrix does not have all n eigenvectors. Then I would call it a defective matrix. And it's got its own connotations and so on. But for the time being, we'll take it to be this way. Yeah. We're going to do that right now. First, I'm going to tell you how to find these U's, and how to find this lambdas, etc. Okay. So let's do it in the 2 by 2 case, simplest case. And let's take one of the Pauli matrices. Let's take one of the Pauli matrices themselves, right? So let's take sigma 3. The reason I'm doing so is to cheat a little bit, because I know that when you have a matrix which is in diagonal form, what's meant by a diagonal matrix? All the other elements are 0 except the principal diagonal. When you have a matrix in that form, it's called a diagonal matrix, and the eigenvalues of a diagonal matrix are just the elements on the eigenvalue on the diagonal. So in this case, the eigenvalues are just +1 and -1. I already know that to start with. Okay. So we would like to find times a column vector. Let me call it U1, U2. It's a 2 by 1 column vector. So let's call it U1 and U2. I don't know U1 and U2. This is equal to lambda times u1, u2. Right? So the equation I have written is this. Let me write the general formula down and then do it in the 2 by 2 case to give the example. So just wait for a second for the example. I will write this as equal to lambda times the unit matrix times u. Does it change anything? Doesn't change anything at all. The reason is I now have n by n matrices on both sides. So it's just more convenient, right? This implies that lambda I minus m on u is equal to 0. I bring this to that side, I take this to that side, and it's lambda I on u acting on u is equal to 0. So I have a matrix acting on this eigenvector, this column vector u, and I get 0 in the null matrix. When will this happen? If this is an n by n matrix, then this u is a column vector which is n by 1. So it's got u1, u2, u3 up to un. And what sort of equations are these for u1, u2, un? Are they linear equations? Yeah, they are linear. They are linear simultaneous equations, right? Are they homogeneous or inhomogeneous? Is there anything on the right hand side? They are homogeneous equations. When do homogeneous equations have a solution? When does this set of equations have a solution? Alpha x plus beta y equal to 0, gamma x plus delta y equal to 0, where alpha, beta, gamma, delta are constants, numbers. When does this set of equations have a solution? There is a criterion, the Cramer's rule. Yeah, but that's stated in terms of a determinant. Determinant of coefficient should be 0, otherwise it doesn't have a solution. And what's the determinant of coefficients? Alpha, beta, gamma, delta should be equal to 0. Right? What does that geometrically imply? Are you familiar with this Cramer's rule? That when you have simultaneous equations, linear simultaneous equations, the inhomogeneous equation has a unique solution and the homogeneous one does not have a solution when the determinant is 0. And when the determinant is 0, the homogeneous set has got a solution and the inhomogeneous set has no solutions. Are you familiar with this? What does it imply to say? It's sad. What does it geometrically imply to say that this set of equations has a solution? What does this quantity represent geometrically on a plane? Line, exactly. What if you had here a constant, let me call it epsilon, let me call it eta. What does it represent geometrically? Two lines. And when would they have a solution? If they intersect. If these guys intersect, they have a unique solution like this, right? What would this imply if these guys are 0? Both these fellows pass through the origin. Both these fellows pass through the origin. And the only solution that they can have, this is the origin, O. The only solution they can have is a trivial solution, x is 0, y is 0. Unless geometrically, what does it mean? What's the only other condition? Unless they lie on each other. Unless they lie on each other, right? If they lie on each other, what kind of solution do they have? How many solutions? Infinite number, everything on that line. So these, and when do they lie on each other? When the determinant is 0. That's all Cramer's rule is. It's completely geometrical. That extends to higher dimensions, any number of independent simultaneous equations, it extends to operators, it extends to Banach spaces, it extends to everything, the Fredholm alternative, etc., etc. But the basic idea is trivial, completely simple. Okay? And when they lie on each other, how many solutions do they have? Infinite solutions. Why is that? What can you find then? Can you find x and y together? That line is given to you. I give you x. Do you know y? Yes, you do. So what you can find is the ratio x is to y. You can't find x and y independently. You can find them up to an arbitrary multiplicative constant. You can find the ratio of the two. So that's exactly what happens here. When will this set of equations have a non-trivial solution? In general, this set of equations has a trivial solution, which means u1 is 0, u2 is 0, all the way to un equal to 0, unless the determinant of this matrix is non-zero, is 0. If the determinant vanishes, then you have the lines lying on top of each other situation. So the solutions are determinant lambda I minus n. You can then find u1, u2, u3, u etc. whatever up to un, up to the ratios. You can find the ratio of u2 to u1, u3 to u1, un to u1, but you can't find u1 itself. One of them you can't find. You can do that by normalization. You can say I want the vector to be a normalized to unity or something. It's obvious from this equation. It's obvious from this equation that if you find u, you multiply u by 22, you still get the same equation. So u is determined only up to an arbitrary multiplicative constant. Another way of saying it is one component of u will determine, the rest will be determined in terms of one component, any one component. Okay. So let's apply our newfound knowledge, this criterion, to the Pauli matrices. We want determinant lambda I minus m equal to 0, that's the magic equation. This is called the secular equation. Determinant lambda I minus sigma 3 is equal to 0. So it's lambda minus 1, 0, 0. That's the equation. I is of course 1, 0, 0, 1 and sigma 3 is 1, 0, 0, minus 1. So this is the determinant. What's the value of the solutions of this equation? Lambda equal to plus minus 1. What happens if I put sigma 2? Lambda here, lambda here. What do I get here and what do I get here? You get I. What's that equal to? What are the solutions equal to? Plus minus? Plus minus I. Lambda equal to I. These are Hermitian matrices. Plus or minus 1. Why I? I times minus I is real number. Is 1 and then because it's the left hand side you got to put a minus there. So it's lambda squared minus 1 equal to 0. So what are lambda? Plus or minus 1. What about sigma 1? What are the eigenvalues? Plus or minus 1. So every lambda, every sigma matrix has eigenvalues plus minus 1. Okay. That's the first magical property. What is sigma 1 squared? Take sigma 1 and square that matrix. Do row by column multiplication. Squaring it, just squaring the diagonal elements. In fact, that's a useful trick to know. If an n by n matrix is diagonal, completely diagonal with diagonal elements lambda 1 to lambda n, then the square of the matrix is just the squares of the diagonal elements. The cube is just the cubes of the diagonal elements. Any function of the matrix is just the function of each diagonal element. So it's an incredibly useful property. So sigma 3 squared you already know is just 1, the identity matrix. What is sigma 1 squared? Unit matrix. So each of these matrices is equal to I. So you see, in the case of matrices, if I ask what's the square root of 1, it's like asking what's the square root of the unit matrix. Is there a matrix such that the square of the 2 by 2 matrix is the identity matrix? That's what I would call 1 in matrices. There's an infinite number of possibilities. Whereas in numbers, there's only 2 possibilities, +1 and -1. Here's an example. Here's a matrix which is different from that, which is different from that, sigma 1, sigma 2, sigma 3. The squares of any one of these is equal to 1, still equal to 1. Okay. What happens if we multiply 2 at a time? Let me write it as sigma I, sigma j. I am sorely tempted now to use tensor notation, to use index notation. I, j, k, etc. will run 1, 2, 3. Repeated indices will get summed over. What is sigma I, sigma j equal to? Well, you have to take I equal to 1, j equal to 2, etc. If I equal to j, of course, it's equal to 1. But if I is not equal to j, when I is not equal to j, sigma 1, sigma 2 will give you I sigma 3. Sigma 3, sigma 1 will give you I sigma 2, and so on. So this is equal to I times epsilon. Let's not use I and j, let's use j and k. I can write it in terms of that Levi-Civita symbol, I times epsilon jkl sigma l, but this is equal to 1 if jkl are in the natural order or an even permutation of it. So sigma j sigma k is I epsilon jkl sigma l. And if you put in 1 and 2, sigma 1 sigma 2 is I sigma 3. Sigma 2 sigma 3 is I sigma 1, and so on in cyclic permutation. Which also turns out to be equal to minus sigma j sigma. So sigma 2 sigma 1 is minus I sigma 3. So what's the commutator? This is what Lakshmibala wrote down the other day. Sigma k equal to sigma j sigma k. Well, you just have to use this. This stands for sigma j sigma k minus sigma k sigma j by definition. That includes what happens if j equal to k. If j equal to k, this vanishes, and j equal to k, this commutator also vanishes. This is why when you multiply both sides by h cross over 2, you get a representation for spin half. Yeah.
Civitas symbol into this.
I didn't get it. I just defined the Levi-Civita symbol. And I'm just saying that I've written, I'm lazy, so I don't want to write sigma 1, sigma 2 equal to sigma 2, sigma 3 equal to, etc. I write it in one line by using this. And you put whatever JKL you want, and it's still valid. Just a compact notation. And what she said was Sx was equal to h cross over 2 sigma 1. Sy is sigma 2 and sigma 3. They are representatives of spin half particles. And then you get the commutation relation, because if you multiply this by h cross over 2 on both sides, you get a 2 here, so you get h cross squared over 4, that becomes h cross over 2 because of the 2 factor in the numerator, and it gets absorbed along with this with a single h cross, and it leads you to the statement that Sx, Sy equal to I h cross is Z, and so on. This is what she called the spin operator commutation relation. And the three relations together form what's called a Lie algebra. She used the word algebra without using Lie because it's technical, but they form the spin algebra. So the sigma matrices form a representation, provide a representation for the spin half spin algebra, angular momentum algebra. But they do a lot of other things as well. They represent many, many different things. One of them is that they represent spin half operators. Okay. As interesting as this is, it's even more interesting because you make it look at the anti-commutator. So look at what happens now if I do the other thing. Sigma j, sigma k, plus sigma k, sigma j. What is this equal to? It's equal to 0, because this is equal to I epsilon jkl, this is minus k. The moment I do this, AB plus BA, AB minus BA for A and B operators is called the commutator of A and B for matrices or operators. AB plus BA is called the anti-commutator. And what's the anti-commutator of the Pauli matrices? 0. All the anti-commutators are 0. That's a great advantage, because now you see, you look at what happens, the power of this. These sigma 1, sigma 2, sigma 3 look so much like the components of a vector. Of course, it's not real vectors in that sense, because they are 2 by 2 matrices. And we are now abstracting, raising a level of abstraction to a stage where I am saying that the components of a vector look like matrices. No problem. As long as I define my quantities properly, there is no problem at all. Let A dot sigma, let A be an ordinary vector with components A1, A2, A3. Let this stand for A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3. Plus. Oh, what's the notation? Yeah, it's a good question. AB. The anti-commutator is defined as AB plus BA in general. There are many different notations for it, but the one I like is this, AB with a plus sign. In many books, you'd also see this notation, curly bracket AB. I don't like this notation. I don't like this notation because in classical dynamics, this is called the Poisson bracket between two functions of phase space variables. So it's already been reserved for something else altogether and is likely to lead to great confusion. So I'd rather write it like this. What's the square of A dot sigma? Well, I have to write this out and square it. Well, the first term will be the square of this guy. What is sigma 1 squared? Square of A1, sigma 1 times I. So there is A1 squared I plus A2 squared I plus A3 squared I plus there is A1, A2, sigma 1, sigma 2. But there is also A1, A2, A1, sigma 2, sigma 1. You have to be very careful. You have to take it in both orders. Pardon me? But sigma 1, sigma 2 plus sigma 2, sigma 1 is 0. Okay, do you appreciate this fact? When you square a matrix like this, you have to be careful. You have to write it a squared, a plus b whole squared is not a squared plus 2ab plus b squared. It's a squared plus b squared plus ab plus ba. Because the order matters. But the anti-commutator is 0. So what do you get here? And if A1, A2, A3 are the components of an ordinary vector, what is A1 squared plus A2 squared plus A3 squared? Magnitude squared. So do you agree that if I give you an arbitrary vector, unit vector A1, A2, A3 components, then this quantity, this matrix squared is just the unit vector? And then infinite number of such possibilities. Every unit vector in three-dimensional space in any direction whatsoever, dotted with the Pauli matrices, will give you a matrix whose square is I. So you have an infinite number of square roots of the unit matrix. And once you do this, the next step is very, very simple. And I'm going to leave that to you. We'll resume it at some other stage. I define the exponential of a n by n matrix. I define it in the following way. Summation n equal to 0 to infinity m to the power n over n factorial. And I state without proof that this series converges very well, it's convergent and makes sense for all matrices, n by n matrices whose elements are finite. All that you need is that no element should be infinite. Then this exponential series defines e to the power n. What is this quantity equal to? Yeah, e to the power m will also be an n by n matrix because it consists of m, which is an n by n matrix, m squared, which is an n by n, identity matrix, which is n by n. All the powers are n by n matrices.
So do we define the operation of raising the matrix to the power of e as this infinite?
It's a deep question. For any arbitrary operator, can I define what's called the exponential map in this fashion? When it can be defined, it's this. Yeah. And it can be defined in a wide variety of circumstances. Not always, but in a huge variety of circumstances. Yeah.
So using this definition, we can define the natural logarithm of a matrix and also a matrix to the power of a matrix.
Yeah, you can do a lot of things like that. Yeah. Yeah. You're already familiar with the exponential of an operator, the differential operator. After all, you're familiar with it, but you don't know that you know it. What is f of x plus a? What's the Taylor series of f of x plus a in terms of f of x? A is some number, some real number, say. Equal to f of x plus a times f prime of x plus a squared by 2 factorial times f double prime of x plus etc. all the way through. I can write this as equal to 1 plus a d over dx plus a squared over 2 factorial d2 over dx2 acting on f of x. Formally I can write it like this, all these operators acting on f of x. But this is an exponential series, e to the power a d over dx. So we found out that f of x plus a is formally e to the a d over dx acting on f of x. So not only do you know differentiation, but you also know how to exponentiate the derivative operator. It stands for that series with all powers of the derivative acting on this f of x. So what's the effect of this exponential derivative acting on f of x? What does it take you from f of x to where? To f of x plus a, right? What kind of shift is that? What kind of operation is that called, moving from one point to another? Translation. So the derivative operator translates. And physically, what does the derivative operator, what operator gives you translation, moves you from one point to another? I have a stone, I kick it, it moves from one point to another. What have I changed? I changed its momentum. I gave it momentum. So the momentum operator translates in space. That is why d over dx is represented by the momentum operator. Why the momentum operator in quantum mechanics is represented by the d over dx. You put in an I here for hermeticity and things like that, but the underlying truth is this. Underlying reason is just this. So everything is connected to everything else, as you can see. So you need to find this, and this will be a generalization of the idea that you already have with complex numbers, namely the formula e to the I theta is cos theta plus I sin theta. You call it somebody's formula. Euler's formula, Laplace's formula, Euler's formula, etc. This is a matrix generalization of Euler's formula. What's going to happen? The first term is I. The next term is a dot sigma. The term after that is a dot sigma the whole squared, but that is this. Therefore, what's a dot sigma the whole cubed? This is just the unit matrix. So apart from some powers of a, it's again a dot sigma. So as you can see, every even power will involve just the unit operator, and every odd power will involve just a dot sigma. Therefore, you can add them all up and join them together, and you get a nice formula. Okay? The formula you get is the following. What is a dot sigma whole cubed? A dot sigma times this. But this I doesn't do anything. So it's a squared times a dot sigma. So this will turn out to be I cos A plus I times sin A by A. Matrix generalization of the Euler formula. Not hard, they follow one after the other, the things would follow from these sigma matrices. So the sigma matrices are really, really very useful in all of physics. Yeah. Okay. Find the commutator of these two matrices. One is A dot sigma and the other is B dot sigma. For A is A1, A2, A3 and B is B1, B2, B3. Two arbitrary vectors in three-dimensional space. Very frequently one needs a combination like this. So find this and you're in for a little surprise. I'll stop here today.